Dr. Matjaž Humar. He's a young researcher, got a PhD in nanosciences and nanotechnology at Joseph Stephan in 2012. So after the PhD, got a position at the Wellman Center for Medicine in US. And then he had the chance to come back. It is not always the case. He had the chance to come back to Joseph Stephan. Now he has a fellowship, a Marie Curie fellowship. And I mean, the seminar tonight will be particularly interesting, and I think will be also easy to understand to many people, because it's a very general topic. During the seminar, Dr. Humar will talk about the results of a recent work he carried out together with some co-workers, I suppose, work in which they demonstrated the possibility of triggering and operating a laser, which normally is a big or even huge device, inside a live human cell, which is, I mean, astonishing. And this, if I correctly understood, was obtained by, let's say, letting the cell kind of eat a special kind of microcavity, which is hosting the laser effect. I mean, of course, then Dr. Humar will provide all the details. And the interesting point is that the light emitted by this very small laser carries detailed information about the particular process undergoing inside the cell, and at the same time, even more intriguing, about the cell itself. So we can imagine the possibility of tagging all the cells of a human body. And this would open the door to fantastic things. For example, understanding the cause and the evolution of a large number of diseases. And I mean, this is the first step towards finding a remedy. So, I mean, I leave the word to the speaker. Of course, after the seminar, we will have a debate. You are kindly invited to, I mean, prepare your questions and also your comments. I mean, not only questions. So we are looking forward to, I mean, really discussing this exciting result and possible applications. So please.
Thank you very much for the introduction, and also thank you for inviting me here. I'm also from Primorska, from near Nova Gorica, Vrtojba, and it's really a pleasure to give a lecture here, and also I see some familiar faces, so yeah, thank you for inviting me. So yeah, as already introduced, I will talk about a little bit more exotic topic, like combining different optical devices like lasers and biological entities. So just to warm you up, so because I'll be talking about like medical applications of, for example, lasers. A few examples what lasers are used for in medicine. They're used for different surgery, like eye surgery, you all know, and you can remove tattoos with laser. Then you can do like imaging, like see through the eye. You have been probably, some of you, to a doctor that you can see, they can probe your eye. And also like for drilling teeth. So this is usual applications. So in these usual applications, how like a laser or some other device is usually used, that is like a machine, big machine, and you this machine is used to treat or diagnose like a patient or some other biological system. So this is the classical way. So you have a laser on one side, and you have a biological system on the other side. But we want to join these two, so to make one. And how is this done? There are like different possibilities. For example, you can put the biological system into the laser. So in this case, you would put a peak into a laser. It sounds funny, and actually a peak is like too big to put in the laser. But you can put, for example, a cell into a laser, and I will show you how. The other way to integrate both these things together is the way around. So you put a laser into the biological thing, so into the human body, for example. And the third option is that you really integrate both together. So the biological entity, it's actually the optical device. It's the laser itself, and it emits like laser light. So just one example. So why we want to do this? Why not to use the classical way? So there are various reasons. The first one is if you have both integrated one into another, you have better coupling between the device and the biological system, so you can get better sensors, and you can get more targeted medical treatments instead of like putting the light from outside if you have already inside. Then these lasers, if they are made from biological things, are biocompatible and biodegradable. And if they are made from cells are small, so they are small miniaturization. And also, if the optical device is made by biological entities, it can self-reproduce, so it can divide like for example, cells. It can self-assemble, it can make evolution, it can adapt itself, it can have self-healing, and also scalable. And the last thing that's like it's more science fiction is new human-robot interfaces. So this is like cyborg thing. And actually, I will show all of these properties, except maybe evolution and adaptation. I will also show cyborg, but not a human, but a peak cyborg. And so my talk is divided into two. First is lasers, and then biocompatible optical waveguides. So I will start with lasers. So usually, as I said, the laser is like a box, and you use for example, medical treatment. But yeah, our idea was to put the whole box into, for example, a cell or a human body. Why we want to do that? And people are already using different light sources, not laser sources, but other light sources inside cells. So these are like different fluorescent probes, and these fluorescent probes are used to stain, for example, cells, and then to make such nice microscopic images and to measure different things inside the cells. So people are already using different light sources inside, for example, cells. But these light sources that are used now, they have very broad emission or absorption spectrum. So this means this is wavelength, so this is blue light, and here is red light, so a rainbow, right, in different wavelengths. And these light sources that are used till now, they have very broad this emission. Like for example, white light has all the colors inside. But on the other hand, we know, from experience, you've seen lasers. Lasers have very precisely defined color. This means they have very sharp peak in the spectrum. So they have just one color. Because you have these very sharp peaks, you can put a lot of them together without overlapping one with each other. And also you can measure very precisely the shift, how this shifts, and you can make a sensor, for example. So what's a laser? Some of you may know, somebody not. So a laser is composed of, first of all, a laser cavity, or it's also called laser resonator. And inside the resonator, for example, two mirrors. the light is trapped and the light resonates. It's almost the same as, for example, you have a flute and inside you have air that resonates, it's closed, or a string on a guitar. And because, for example, a string then can oscillate in different modes, and these are well-defined oscillations, and this defines these very sharp lines, or actually wavelengths. So this is the cavity, and then you have a gain medium. So the light that is trapped inside the cavity has to be amplified, and this is amplified by some gain medium, and this gain medium is it can be different things. It can be a crystal, it can be a fluorescent dye, and I will talk about fluorescent dyes as a gain medium to amplify the light inside. And the third thing that you need is a pump. It's called a pump because you pump with energy, so you need a source of energy. And this can be electricity, it can be some other source of light, for example. So this is basically our laser, and we want to make all these components out of biological constituents. And just to start with, his example is the first example that you put the peak into the laser, but here we put a cell into a laser, and this laser is like 2 mirrors, and the light here gets amplified by the cell because the cell has inside fluorescent protein. And you get light coming out of the cell, and this fluorescent protein is so some animals they have this fluorescent protein, and it's put inside the cell. And what you can do with such laser with the cell inside the laser cavity. This is if we look from the top, how the light comes out of the laser. It's not just a point like this my laser pointer, but it has different more like beams, laser beams with different shape. And from the shape of these beams, you can actually characterize the cells, like the shape, the refractive index, the distribution of molecules inside the cell. And if you make some change to the cell, you can see that this pattern changes. So you can use this as a sensor, and it's very precise sensor because the light is amplified inside the laser. We were thinking, we put a cell into the laser, but now we were thinking how to make the laser to put inside really the cell. And for my PhD, I was working on small lasers. These are so-called whispering gallery mode lasers. And if you have a small sphere, it can be droplet or solid sphere, the light can be trapped inside due to total internal reflection. So just inside the very small sphere, the light is trapped and circulates inside. And this makes the laser cavity. So instead of a linear laser cavity, like I was showing, like 2 mirrors, you can have a sphere. And that's why you can make this very small. And inside this sphere, you have fluorescent dye, which is the gain medium, amplifies the light. And our idea was to put these lasers inside the cell. And we have published this, and I will talk about this more into detail. So how is this done? It's actually very easy. It was like one-day experiment. We just took fluorescent particles, spheres. These are commercially available. You can buy them. And they already have green dye inside. And you just put to the cells, live cells, and these live cells eat the particles. And here you see multiple cells, and they have these particles inside. And you have a laser inside. So how you look at these lasers? With a simple setup, this is actually a microscope. And we have these beads in cells. And then we have an external light source. This is either an LED or another laser that you excite the dye inside the small lasers, and the laser light that is generated here goes to either the spectrometer, you can see the spectrum, these sharp peaks, or to the camera and you can see the cells. In reality, it's a little bit more complicated. You can have multiple lasers, you can manipulate these beats and so on, and everything is controlled by computer. I will not go into details, but in the lab, it looks like this. So it's a microscope, spectrometer, and some other devices. So how does it look, this spectrum from the cell that's lasing? So for just normal dyes or like for these light bulbs, you would have like this very broad emission. But for the laser, you have these very sharp lines. And if you pump with more energy, the laser, you get higher and higher, and with these very, very sharp lines. Typical lasers, they have usually just one line in the spectrum, but here we have more of them, just another type of laser. And we can also see if we increase the power, there is some threshold, so-called laser threshold. So with this, you can really say that it's lasing. I will not go into details, but below the threshold, you don't have any lasing, and then suddenly you get lasing. So what you can do with these small lasers? Here there is an image of multiple cells on the surface, and for example, this is one cell, and it has 3 lasers inside. And then what we took, we made a hyperspectral image. That means this is actually a movie, and it's not playing in time, but in wavelength. So this means that each frame is a different wavelength, different color. And you can see that each beat is like blinking, each laser. This is because we are playing over the wavelength, and for each peak, we see this blinking. You can see the different size of the beat of the laser blinks in a different way. And actually from this signal that comes out of each laser, you can fit to a model, to a theory, and you can calculate very precisely the size of the laser. And you can do this really precisely. This is a laser, it's 8.5 microns big. This is like 10 times smaller than the width of your hair. But you can calculate the diameter, the precision is like below 1 nanometer. So it's like 1 atom or 2 atoms precision. And you can do this on multiple beats inside cells. So why would we need this so high precision? You can see that each bit has a different diameter, different number. And you can use this number as a barcode, as an address. So how is this done? That each bit that is a little bit larger is a different barcode. And usually you cannot, with cells, they're so small you cannot put a sticker onto it or something to tag it that you know this is cell number 1, 2, 3, 4, 5, and so on. But with this bit, because you can measure so precisely the size, you can use the size as a barcode. And you can read this barcode just like in a shop that you have this barcode reader. Here, similarly, you have a laser, you shine in, and you get some signal, and you measure with spectrometer. And in this case, you can get 2,000 different sizes that you can distinguish. But you can also use different colors of these beats, and you can, for example, use 10 different colors. Then you have 2,000 by 10. It's already 20,000 different addresses. And what you can do more, it's actually because each cell can contain multiple these lasers, and actually you can calculate the number of combinations, the possible barcodes, if you take three bits inside, and it's 10 to the 12. So this is trillion different combinations. And actually, in the human body, we have approximately this number of cells. So with this method, you can tag individually each individual cell in the human body with a unique tag. And this is useful, for example, for tracking cells, how they move in the body, for example, cancer metastasis, or just in the lab to track each individual cell where it goes. And this was impossible till now just with using just dyes, because dyes you can use, for example, just 10 different dyes. Another thing that you can use these lasers is for the sensors inside cells. So these lasers are very sensitive to the environment, to the surrounding of the cell. And if you make some change to the cell, like putting more sodium chloride, so more salt to the cell, you can do some change, and you can see this change very precisely. And this is much more precise than any other, almost any other method, because we have these very sharp lines. So in this way, you can measure, for example, the different chemicals and different processes inside the cell. So this is another use. So till now I was talking about solid lasers, like spheres. But what you can do, you can also inject inside the cells. You can inject oil droplets. So these are liquid droplets. And again, you have a dye, fluorescent dye inside the droplets, and you can make lasers also from these droplets. Now, what is the difference between the solid lasers? The solid lasers were made from different, like polymers, so they cannot be deformed. But this, because there is just a droplet of oil inside the cell, can be deformed by the forces inside the cell. So the cell moves, it divides, and it has different processes going on inside the cell. So there are forces inside, and we want to understand these forces, how the cell moves around and so on. And if this droplet it's deformed by the forces, you can observe this in the spectrum of the emitted light, of the laser light. And instead of just having individual peaks, you get these small peaks. And from the distance between these peaks, you can approximate how much this droplet was deformed, and you can measure actually the force inside the cell. And you can do this very precisely, probably better than any other method available. So this is another great tool for studying the processes inside the cells. So I was talking about artificial lasers, so beads that you put to the cells or you can inject. So now the question arises, is there in the human body already lasers available? And the answer is yes. These are so-called adipocytes or fat cells. So we all have fat, and the fat cells contain huge droplets of oil. And if we extract these cells out, we just put a dye to the cells and we excite them and we get lasing. So these are natural lasers that we already have inside the body. And it actually works also in the tissue. So I have a piece of tissue from a pig, and first I inject it inside dye, and now I go with this optical fiber to excite the lasers inside, and then to collect light, laser light. And this is a spectrum, and you can see these sharp lines. So these lasers also work inside our body, and they're already present inside. So actually we made something like this, so a laser inside us, right? But actually it's not like this, it's actually from fat, right? It's not from the eyes, it's from the fat. So next time when you go to the gym or running, you can say, I want to get rid of some lasers. So instead of get rid of fat, you can get rid of the lasers. And this work that I was talking till now got huge outreach in the media, like all the best journals and also popular news, and also in Slovenia was on Dnevnik, and I also become ime tedna and Osebnost Primorske for July. So it was really it's interesting also for general public. So we continue this work here in Slovenia at the Stefan Institute, and one work is to make lasers, artificial lasers, but made from substances that are already used in medicine. That's why if you use already some substances that are allowed for use, you can inject in the body, and we use some polymers and dyes that are used, and we can make these small lasers. And what we can do, for example, is implant them into skin, and we actually use a tattoo gun. So this is actually really for making tattoos. But instead of the usual dyes, usually ink that we use, instead of that ink we use small lasers, and we implant them into skin, and we can make different patterns. And then this is an image of such laser inside the skin. Actually, you cannot see this sphere because it's below the skin, but if you measure the spectrum, you can see these peaks. So it's really lasing inside the skin. So this is so-called, I call this laser tattoo. So if you want one, you can come to the lab. We can try on you. Then another kind of laser that we made is from liquid crystals. I will not go into details, but liquid crystals, the molecules of liquid crystals, they order themselves, so self-assembly. They order them in such periodic fashion, and because of this periodicity, here you can see this is a droplet of a liquid crystal. It's very ordered. You can also make a laser, and this laser emits from the center out. This is just how it looks like. So this is a droplet, and then you excite the laser, and then it emits in all the directions. We call this 3D laser. What we did is to make this 3D laser out of cholesterol. So cholesterol is, everyone says, is bad for us, but it's good for lasers. So cholesterol also assembles in these droplets with this nice periodic structure, and you can make a laser. And in this case, the laser has just one line, one color. Because before I was showing multiple peaks, this one has just one line. And one example that it can be used, for example, for measuring temperature inside the body, or also some chemicals. And because it's made from cholesterol that is already present in our body, it's non-toxic. I mean, not in high quantities, but if you inject a little bit of cholesterol, it's okay. So we made, I was talking about laser cavity, also natural laser cavity made from biological stuff, biocompatible and so on. So what about gain material to amplify light? All the lasers that I was talking till now, they have some artificial fluorescent dye inside. So we have to inject some dye. So how can we make this gain material from biological? You can use green fluorescent protein. I was telling in the beginning a little bit. Green fluorescent protein is nothing else, just is a natural fluorescent dye that can be produced inside the cells. And if you coat this, put on the surface of these lasers, this natural dye, you can also make a laser. And just an example, what we use this for, it was inside a cell, and this cell divided into two cells, and the laser went into one cell. And then during this division, we were observing the emission of the laser, and you can see a clear jump in the modes when the cell divided. So you can measure like some changes inside the cell in this way. So we have natural laser cavity inside fat cells, so these droplets, and we can now combine these droplets with natural fluorescent proteins, so natural dye. So we have both gain and both laser cavity droplet together. And how we did this, we engineered a protein, like a genetic code, and we genetically modified cells. And the cells produce this green fluorescent protein. And this fluorescent protein is engineered in such a way that it goes onto the surface of the droplets. So it self-assembles onto the droplet. So you have both droplet laser cavity resonator, and you have on the surface you have gain, which amplifies the light. And one property of such lasers is that they self-healing. So because everything is made from biological stuff, if you damage a little bit, after some hours it returns, it produces again this fluorescent protein. So it's a self-healing laser. It's also a living laser, right? Because it's a cell and it can be divided into multiple cells. And everything is produced within the cell. So we have gain. Now, what about source of energy? So this laser that I was talking about now before, you always need a source of light from outside to excite, to activate the lasers. So what about some natural light source? So what's the natural light source? It's bioluminescence. So you've all seen fireflies, or in the sea, you can see this bioluminescence, light produced by nature. And how this works, it's just a chemical reaction between two molecules that are produced naturally inside the animals. And now, can we this use for our lasers? We'll just skip this. So yes, you can use, and you coat these molecules onto the surface of our lasers, or they can be produced inside the cell. This is, for example, an image of these small lasers, and there is no light from outside. This is just light generated by the chemical reaction, biological generated light. And inside the spectrum, you have these sharp peaks. Just a detail that actually this is not truly a laser, but it has a laser-like emission. The light is similar as the light of a laser, and you can use it in the same way as the lasers, like for tagging, for sensing, as a sensor, and so on. So we have all components made from biological constituents. So this was my first part, and the second part is about waveguides. So actually there is a problem with all these lasers. It's that our body is not transparent. So you cannot see inside your bones and veins and so on. You can see just like 1 millimeter in depth. So light doesn't go deep into the body. This is a problem. And there are different methods that you can go deeper inside, but still 1 centimeter or a few millimeters, it's not enough. The only way of going with the light really more deep inside is optical fiber. So like optical fibers for internet, right? But usually optical fibers are made from glass or plastics that is you can put in the body, but you have to remove soon afterwards. They cannot remain inside. So what we have done is to make this kind of fibers out of materials that are allowed for use in medicine. So these materials are used for medical implants and stitching and so on. And they're just some polymers, nothing really special. But we made this for the first time. And actually, if you compare how much the light propagates inside the tissue, this is like how much the light goes in. So just if we shine onto the surface, it propagates very little. But if we put optical fiber inside, you can go very deep into the tissue. And what are possible use of this? So one use is so-called photochemical tissue bonding. So if you have a wound, like surgery or some other thing, what usually doctors, they use a suture, like they suture you up, and usually the stitches that they make, they leave scars. Another way to make a stitch is by laser. You put some dye onto the surface and you shine with the laser, and the tissue gets glued together, so it's just a glue. And this works very nicely, and it's already in testing, like clinical trials. But there is one problem, that you cannot close the wounds, very deep wounds, because, as I said, the light doesn't propagate so deep inside. We made such waveguides that you can propagate inside more deep into the tissue, and this is how it looks like, the experiment. This is a pig, again a pig, on a surgical table, and we made a cut, put some dye inside, we put the optical fiber, and we shine with the light inside. And afterwards, after the procedure, this takes just a few minutes, you just cut away the fibers, because if you would put out, then there would be holes inside. But because these optical waveguides fibers are made from biodegradable material, you can leave them inside, and they just degrade over time and close the wounds. And yeah, this is how one application. And actually, this was very again interesting for the general public. And I guess some of you know Mythbusters, yes. Tore from Mythbusters, he came to our lab in the surgical room to shoot I think it already should be on Netflix, the White Rabbit project. Yeah, we were shooting some scenes how you can glue the wounds with laser light. Another application that we tried is to kill bacteria. So you know that bacteria, some of the bacteria can be, you cannot treat them with antibiotics. They're antibiotic resistant. One way of doing this, you can use light to kill them. Blue light therapy, it's called. But again, the problem is that light doesn't penetrate deep inside the body, so you can use just really surface. But there are some skin like infections, a little bit more deep, that you could treat. And what we did is that this is the skin. We put needles, optical needles, and we shine light inside and deeper inside the tissue, the skin, and we can treat the whole thickness of the skin in this way. And this is how, just a simulation, how without needles, the light penetrates just a little bit, but with needles you can go more deep inside the tissue. And it's very easy to make these tissues, needles, just by molds, and this is some like polymer. And the idea here is that this polymer is also biodegradable. So imagine if you would have these needles made out of glass, and then you would stick this, and then maybe some of them would break off, and you would end up with glass in your skin. So this doesn't work. But with these ones, if they stay inside, it will just degrade in a few days by itself. So this was the idea. And this is just one example how these two images are without needles. Like it was a thin piece of tissue, and with needles you have much higher transmission of light into the target depth when these bacteria are. And we made also some like longer optical fibers. Till now I was showing like short ones. You can make very long ones. And these were made from hydrogels. And hydrogels contain a lot of water inside, and you can, inside this fiber, you can put different drugs. You can put like cells. So when you put the optical fiber inside, this fiber can also release some drug into the body, and this drug can be also activated by light. And this is so-called light-activated drugs, because usually, you know, if you take a pill or they make an injection, the drug goes into the whole body and can act on the whole body, and it has side effects. But there are some drugs that only get activated by light. And if you can shine the light very precisely on some part of the tissue, like for example on cancer or tumor, you can activate the drug only there, and it acts only there, and it doesn't have toxic effect in the whole body. And one way is to activate this by putting the fiber inside the body, or by using also the laser that I was showing before to activate the drug very locally. And just one example of application is to measure oxygen in the body. I guess you've seen this tube doctors put on your finger to measure oxygen and pulse. But you can do this only on the finger because it's a little bit transparent, it goes right through, but you cannot put inside the body, deeper inside the body. So in this case we put optical fiber inside, and actually in the liver of the mouse, and by light, how much light it's transmitted out, you can actually observe how much oxygen is inside some organ. For example, if you transplant the organ, then you want to know if there is enough oxygen in the organ, and this is one way of measuring this. And actually, this is all I wanted to present. So most of the work was done on Harvard Medical School in the United States with a large group, and we continue the work also here at Jožef Stefan Institute. And we also have a Facebook page, so if you are more interested into this topic, you can like this page, you write down, and you will get all the news, what's going on. And I'm also building my own lab now at Jožef Stefan Institute, and we'll also need some people to collaborate or work in this lab. And thank you for your attention.
I'm just interested, whose was the original idea? Was it yours or Institute Jožef Stefan, or somewhere to make a cell laser, optic fire cell laser? I had difficulties reading just the abstract. I was making laser, laser, and somehow dimensions, wavelengths didn't go into my head. Now I'm convinced.
So. Before going to Harvard, to US, I didn't work anything with biological stuff, but I was interested in this direction. So I saw one paper that this group that I went to, they put a cell inside the laser, this first examples that I was showing. And I said, maybe I can put inside. And also at that time it was known that, some people were thinking about this, but with my knowledge from my PhD, when I was making these small lasers, so I could then implant inside. But I didn't know anything about biology when I came there, so I had to learn everything. So also actually the first month when I came there, they put me into the surgery room with the pick, and then here you cut. I had to learn a lot.
First of all, from a technical point of view, you say that this is a laser. In fact, you show that, compared to other sources, you have a quite narrow peak in wavelength. But normally, this is not enough to say that you have a laser. So the question is, did you characterize the light itself that you can get out of a cell? in terms of coherence, in terms of, I mean, all the properties that make some light laser light.
Yeah, good question. The best way to really prove that it's lasing is to see the lasing threshold, so non-linearity. That I was showing that.
In this curve that where you have
yeah.
this non-linear transition.
Yes, and it's already known, like these beads that you can buy, it's already known that they produce laser light. So what we did is just to put into the cells.
Okay, and then for the cells, you said that just, I mean, you put these microcavities into an environment where you have cells. Then the cells eat them. And then you have light emission, and from the spectrum you can reconstruct a kind of dimension. Is it correct?
Yes.
So, but what I didn't understand, I mean, you can reconstruct the dimension of this microcavity, which is not the dimension of the cell, because, I mean, this microcavity is inside the cell.
Yes, the size of the laser you measure, yes.
So, where is the, I mean, the footprint of the cell in this? Because I understood that you can also say something about the cell itself. While now I'm confused because it seems to me that you can say something about this microcavity that you put inside, which is the same for all cells. Sorry? Yeah, oil drops, you mean that is taking all the volume or what? Okay, this is the second, yes.
Yeah, so you measure very precisely the diameter, but actually this diameter fluctuates because of the surrounding. So if you change the refractive index of the surrounding,
just for me to understand,
of the laser.
You put a droplet in this case.
Yeah, this is solid sphere. Yeah.
Okay, so if it is a solid, I don't understand how this solid is adapting to the cell, because
no, it's not adapting because it's solid. It deforms very little bit.
Okay.
But because the light circulates close to the surface, you have some evanescent fields on the outside, and if you change the refractive index on the outside, it changes the optical path around the droplet. So it changes kind of the diameter or refractive index, and the measured diameter changes. It changes a little bit, and you can, from that you can calculate what's the refractive index outside.
And the refractive index is telling you something about the dimension or about the kind of cell you have? Because the refractive index is also depending on the, I mean, on
the refractive index is depending on the, no, it depends on the what you have in the cell. So the amount of proteins dissolved in the cell cytoplasm. So you can determine like the concentration of the constituents inside the cell. You can also functionalize the surface of the bead with some like antibodies, and you can when some proteins attach to the surface, you can see also a small shift in the laser modes. So you can very specifically also detect specific proteins, for example.
Questions, or I mean, that's your
oil drops? The case of the oil drops in the cell. So here you can also determine the dimension of the cell. Yeah.
Yeah, here you determine basically if you say that this droplet is deformed like into an ellipsoid as a approximation, then you can measure both axes. So not just the diameter, but one diameter and the other diameter. So you can measure both of them, and then you know how much does it deform. But because these droplets deform like all the time, you cannot use this for tagging of cells because they're sensitive to the environment.
I have a question about can this method be used for treating, let's say, tumors which are in places difficult to be reached by surgery, for example?
Yes, but not by the lasers themselves. You still need to get the light in. So in that case, you still need optical fiber. You need some kind of surgery to insert inside. But people are also using bioluminescence to generate the light like locally. That's also one option.
Very nice talk. I'm interested when you show how you stitch together the skin, the wound.
Mm-hmm.
So there you shine with light. Do you burn the skin? Do you melt? Or do you stimulate some growth? Or can you tell us a little bit more?
What you do is actually activate bonds in collagen molecules. Collagen molecules are in our tissues as a they make the tissues like elastic, strong, and with the dye and laser you just activate the bonds in the tissue, and the tissue just glues together. So actually there is no glue, but it's just activation of the bonds, and you glue together. So that's why then afterwards it can heal much faster.
Yes, Sergei Kruzhevich. So as far as I understand, one of principal points for you is how does the light propagate inside the tissue? And so do you have any mathematical model for this, like Ising model? Is it applicable for this case, or percolation or something like this? You mentioned Monte Carlo method, but so are there any mathematical models which work properly for this problem?
The simulations that we did, we just had a simple model of light scattering and absorption inside tissue. It's a simple model and ray tracing, Monte Carlo simulation. Nothing special.
Okay,
just
we can
commercial
discuss it later.
software, commercial software.
Okay, thank you.
When you insert the beads in the cells, do you have any control? How do you know that more than one bead is not absorbed by the cell? Do you insert them mechanically, or?
The droplets you inject one by one, but the droplets you just put to the cells and they eat them. And actually, most of the time they eat more of them. And which is actually even better because, as I showed you, you have then more different combinations. So just with one bead as a tag, you have approximately 20,000, but if you have more of them, you have more possible combinations.
But you don't have any control over how many tags the cell eats?
It's just probability. If you put more of them, then in average they have larger quantity inside, but you cannot control exactly the number. Yes.
No, can you make some sorts of future application? Do you have some ideas what?
For now, mostly the applications are for research. For example, I showed many different what you can do. For example, tagging is maybe really currently the most developed, and you can use this in the lab. So you tag cells, you do some experiments with them, and you read back. So you know which cell which is which because they have a barcode onto them, and you when you do the experiment, then you know how each cell changed. And before this was not possible. They were doing just large quantities of cells, like population of cells. But in this way, you can do individual one. You know which one is which.
What is the typical intensity of these living cell lasers?
Mm-hmm. Actually, you can see with your eye, like very faint. Usually, it's like in nanowatt range.
More? Yeah, sure.
So my question is, in the first part you said you basically input some nanoparticles, and do you have any information what happens in the long term? If these particles remain inside the cell, do they damage it, or is completely safe? Would you put it in your body, if you rephrase it? Thank you.
Yeah, we didn't study like a very long time, but in short term, these cells, they're happy, they divide and they survive. We measured that like 99% of the cells survive. But because these bits are, some of them, they're quite large. They're like this is the cell and then it's a bit, it's a huge one. Probably they change somehow the properties of the cell. But we are also working on smaller lasers. You can make them like below 1 micron. So the cell is approximately 20 microns. So in this case, the bit is 10 microns, so it's half of the size, but you can go 10 times less. And also, for example, putting things inside cells, for example, tattoos are such example. When you make a tattoo, a normal one, the cells eat the dye particles, and they remain inside the cells. That's also why the tattoo is permanent, because the dye goes into the cell, and the cell just survive for a very long time and then divide.
More? If not, I have another one. So I understood how you, I mean, when you say that there is a laser inside the cell, I mean, you mean that something is missing because you need something to activate, no? So, and I understood how you can activate also in deep, because you cannot just send light from outside because light is absorbed. What is not clear to me is the vice versa. So when you activate inside the body, then you have to extract the light. And the light, the light comes out, is absorbed by other cells. So first of all, how you can make it. And second, so suppose that you have the emission of many cells. So you have also interference between them. And if you don't have any relation between the cells, I mean, this interference may be destructive interference. So you may just destroy the signal you want to acquire. And I mean, last, is it possible to exploit instead this fact in order to build a kind of coherent effect? So if you have emission from different cells that are instead coherently linked, I mean, suppose that, I don't know if it is just stupid, but suppose that you have cells that are doing the same thing, just with a coherent difference of phase, and they are emitting light. This light can, in principle, sum up, and so you may have a kind of increase of the signal, and this can also provide information about any coherent phenomenon inside the body. So I mean, it's a lot of things, but I don't know if you can comment on, on some of that.
So the first question. So I explained two ways of overcome the absorption and scattering the tissue. So one is with optical fiber. And if you implant optical fiber, you can excite the lasers, and you can also collect the light from the lasers. So it's both direction. It's not a problem like this one. This one, the fiber. So it goes in both directions. And the other is bioluminescence, where you create really light inside. In that case, the light doesn't come out if it is deep, yes. But if you want to use this light for some treatments inside, it doesn't need to come out.
Yes.
If it remains inside, this is okay. Okay, then about coherence.
I don't know if it is something reasonable.
Yeah, usually
so I mean,
each
just to explain in simple words, light is a kind of wave. So if you have many waves that are coming up together and there is no phase relation between them, I mean, basically you have a flat sea. But if you can in some way put these waves in phase, so they sum up and in the end you may have, something interesting. But I don't know if it is. Here is, this is possible if you have a kind of geometry in your sample. Here, in principle, you don't have any geometry, so maybe it's not so easy, or maybe yes, I don't know.
Okay, so another way of explaining this, so different lasers, they blink in different way, right? They also have different these lines. And if you take the light of all of them together, they just sum up all of this and you get a mess, so you don't see anything. So usually to observe these lasers, you need a microscope to then take the spectra from individual ones. Or actually, if you go with a fiber inside, usually just the laser that is closest to the fiber will then emit light. But you can also use they have different peaks, even if you cannot see them. So that if they are below, like more deep inside, you get light from all of them out of the skin. But from the spectrum, because you have multiple peaks, you can actually determine, even if you don't see them, you can also say how many are there. Or actually, based on the spectrum, you can also determine a little bit positions where they are. So this is also useful in this way.
Okay.
You said that these cells basically eat these lasers.
Mm-hmm.
But why would they eat them? It's polystyrene, it's styropor and glass and too.
Yeah, they think it's a foreign object. So if some foreign object comes into your body, the cells want to destroy it. So they eat, and actually they expose inside with some actually peroxide. They expose the bit to
so you
the foreign object and want to destroy them.
You cannot control what will one cell eat.
Yeah, partially you can by making different surface of the bit. If you put some chemicals on the surface, the cells will eat. If you don't put these chemicals or some other chemicals, they will not eat.
But
you can a little bit control.
Basically, these are passive laser. They just get laser light in and then emit.
Yes, you need a source of energy from the outside, but here you cannot put wires inside, so you use some other light from the outside to activate them, yes.
Mm-hmm. So
with light you deliver energy.
Basically, these are some kind of mirrors that emit only one short wavelength.
Mm-hmm.
Mm-hmm. Okay, thank you.
More? So if not, we just thanks Matjaž again. And I mean, of course, for I suppose that